Dear students, I am Ramesh, chemistry faculty from Vidya Mandir Metric Higher Secondary School, Uttangarai. Let us discuss reverse osmosis. Now, the experimental setup of osmosis. So, here the experimental setup of osmosis. And here we are taking the U-tube. We are taking a U-tube. And in a U-tube, we are filling the high and low concentration. Now, we are taking the semi-permeable membrane. It is semi-permeable membrane made up of polyamide or cellulose acetate. So, it is a semi-permeable membrane which is made up of cellulose acetate or polyamide. Now, here we may fill up with that NaCl solution, sodium chloride solution. So, here it is sodium chloride solution. So, here we are taking that is a sodium chloride solution. And we are taking the particle sodium and that chloride. Sodium and that chloride. And here we are taking the water. Water particle is taken in this so that it is taken as that is a solvent. It is a solvent. Now, what do you mean by osmosis? Osmosis is a process. Here, the solvent particle move from lowest concentration to high concentration. So, the solvent particle move from lowest to highest concentration through the semi-permeable membrane which is known as osmosis. Then the pressure which is known as that is osmotic pressure. Osmotic pressure. Now, we are taking that reverse osmosis. And here in a solution side we apply the external pressure. We apply the external pressure in that solution side. Then what will happen? Here the osmosis is reversed. What is that reverse osmosis? Here the solvent particle move from highest concentration to lowest concentration through the semi-permeable membrane which is known as reverse osmosis. By applying external pressure, we are applying pressure, external pressure, so the pure solvent molecule move from high to low. Now, it is known as reverse osmosis. Now, we may take the uses of reverse osmosis. Uses of reverse osmosis. And here, purification of water, and also desalination of water. So the second use, it is desalination of water. Desalination of water. It is a very simple experiment. We are taking the reverse osmosis. Now we are taking a U-tube. And here we are taking the U-tube, and here we are taking that is seawater here. Seawater here. So here we are taking that is seawater. Now here the calcium, magnesium and the ions are present. Now we are inserting the semi-permeable membrane. Semi-permeable membrane. Now, on the other side, we are taking that is some pure water. So, here we are taking that is pure water. So pure water is taken one side and other side the sea water is taken, and now we apply the external pressure. We apply the external pressure. So the pressure is applied. Pressure is applied. Then what happened here? From the seawater, the pure water present in a seawater move through a semi-permeable membrane. Then we may get the pure water. Then it is known as reverse osmosis. It is a reverse osmosis by applying external pressure. The pure solvent molecule, here the solvent molecule will move through the semi-permeable membrane. Then we may get the pure water. So the pure water is collected. Now we may take this semi-permeable membrane. It is semi-permeable membrane. Semi-permeable membrane. And the semi-permeable membrane is taken depending on nature of the solution we are taken. And the semi-permeable membrane may be, that is cellulose acetate. Cellulose acetate. So cellulose acetate, or that is polyamide. Polyamide as a semi-permeable membrane we are taken mostly. So it is reverse osmosis. Now we are take abnormal molar mass using colligative properties. Colligative properties does not consider association or dissociation of a solute particle. So it does not consider association or dissociation of a solute particle. So normal determination of molar mass using colligative property. We does not consider the association or dissociation of a solute. Now what will happen? Here there is a deviation in actual molar mass and after the association and the dissociation. That is known as abnormal molar mass. So here the association or dissociation occurs. Association or dissociation occurs there is a deviation in molar mass. There is a deviation in molar mass using colligative property. Then this deviation, which is known as abnormal molar mass. So this deviation is called abnormal molar mass. Abnormal molar mass. If you are taken that is association of a solute particle. So what is the deviation? So we are take association of solute particle. Then some solute particle get associated and become dimer or trimer. Suppose if you are taking that acetic acid, that is CH3COOH, and acetic acid in benzene. Acetic acid in benzene. Now acetic acid is associated and become that dimer. So we may take an association CH3 and double bond O and that OH. And one more molecule, it is CH3 bond C, double bond O and the OH. Now, this is acetic acid and it is also acetic acid. Due to intermolecular hydrogen bond, it get associated. It is nothing but intermolecular hydrogen bond. So, it get associated and become dimer. And you know that colligative property, it depends number of solute particle present in a solution. So, if you are taking colligative property depends number of solute particle present in the solution. So, it depends number of solute particle. Number of solute particle present in a solution. And if the solute particle get associated and become dimer or trimer, what will happen? The colligative property decreases. So, by association, colligative property decreases so that the molar mass in association will increases. Molar mass calculated using colligative property is higher than that of actual molar mass. So it is actual molar mass. So, on dissociation, the molar mass calculated using colligative property is higher than that of actual molar mass. So, the molar mass calculated using colligative property of acetic acid, molar mass of acetic acid using colligative 120. So, molar mass calculated by using colligative property is 120. Actual molar mass of acetic acid is 60. So, here calculated molar mass is higher because of association of acetic acid. Now, dissociation of solute particle. Now, we may take that the strong electrolyte like KCl and sodium chloride NaCl is completely dissociated. In solution. So, it is completely dissociated in solution. Now, the molar mass calculated using colligative property, here it is completely dissociated. So, the molar mass calculated by this type using colligative property is lower than actual molar mass. So, if it is dissociation occurs, the molar mass calculated using colligative property is lower than that of the actual molar mass. Suppose we are taking that is here we are taking 1 mole of sodium chloride. It is dissociated, it will be formed Na plus, that is 1 mole of sodium ion, and Cl minus, that is 1 mole of chloride ion. So, there is a dissociation occurs. So, the colligative property will increases because it's dependent the number of ions or molecules present in a solution. And if it is 2 moles, 2 ion is present, then the colligative property increases. So, if we are taking that, the calculated molar mass of NaCl using colligative property is 29.2 and actual molar mass of NaCl is 58.4. So, it has decreases. So, calculated molar mass using colligative property will decreases than that of the actual molar mass. Is want of factor. And molar mass calculation using colligative property for dissociation there is a decrease in molar mass. So for dissociation decrease in molar mass. For association increase in molar mass. For that purpose, we are taking that the factor I. Want of introduced the factor I, which is known as want of factor. And the want of factor is defined as, that is I, is a ratio of actual molar mass to abnormal molar mass. Is nothing but want of factor, and it is nothing but observed colligative property by calculated colligative property. It is observed colligative property by calculated colligative property. Want of factor for acetic acid CH3COOH is 0.5. Want of factor for NaCl is 2. I is equal to 1 if there is no dissociation or association occurs. So, it is for no dissociation or association. Then, here I is less than 1, for association. And I is greater than 1 and for dissociation. So here acetic acid get associated so that it is less than 1 and sodium chloride get dissociated so that it is greater than 1. Now we are take the degree of dissociation or association with want of factor. So first one, that is degree of dissociation. Degree of dissociation is equal to I minus 1 by n minus 1. And here I is nothing but want of factor. And n represents number of ions formed on dissociation. Now, we may take that is degree of association. Degree of association. Degree of association is equal to 1 minus I into n divided by n minus 1. And here also I is Van't-Hoff factor, and here n represents number of ions or molecule get associated. So number of molecule get associated. Colligative property related with Van't-Hoff factor. Van't-Hoff factor. And you know that the first colligative property one is lowering of vapor pressure. So, lowering of vapor pressure is P naught minus P divided by P naught, which is equal to I into N of solute by N of solvent. Now, the second colligative property, depression of freezing point, is delta TF, which is equal to Van't-Hoff factor into, that is KB into molality. Then the third one, it is elevation of boiling point. Elevation of boiling point. Then elevation of boiling point is delta TB. Is elevation of boiling point, which is equal to Van't-Hoff factor I into, that is KF into M. And the fourth one, that is osmotic pressure. Osmotic pressure. So, osmotic pressure, that is pi, which is equal to, that is weight of a solute by V into RT by molecular mass of a solute. So, osmotic pressure pi, which is equal to Van't-Hoff factor I into, that is weight of a solute by volume into RT by molecular mass of a solute. So, we may modify the 4 colligative property with this Van't-Hoff factor. Thank you.